Hey there, Stat Nation. Welcome to Chapter 9, Day 4. We're talking about error types, Type 1 and Type 2 errors. So these concepts can be very, very complicated, even though they're somewhat simple when you first see them. But the way the questions can be asked on the AP test can be complex. Okay, so a lot of this comes from common sense. So when you are doing a test for something, so let's say that we are trying to figure out if a certain drug's claim is true, like um, let's just take um, headache medicine. The medicine says it'll get rid of your headache in 5 minutes on average. Okay, 5 minutes, fine. And we do a test of 100 people and we find out that it's 5.1 minutes on average. And the question is our test that we did evidence to reject their claim? Their claim is 5 minutes. So there's basically four things that can happen in any kind of test. You can say, I don't believe that claim is true with your evidence, and eventually it is found out that you're right. You can also say, I don't believe that claim, and you're eventually found that that's wrong. That's an error type. Okay. Or you can say, I do believe the claim is true, and you can be correct eventually. Or you can say, I don't believe it's true, and you can be found out to be wrong, and that's an error. So there's four decisions that can be made in anything. Okay, so let's look at it right here. All right, so let me get the pencil. There we go. Okay, so if you have HO and HA, okay, so let's do something really simple. HO, we will say, is you are innocent. Let's just take a court case, which everyone understands from the beginning. HO is innocent. That's always the assumption. And HO is called H null, which is called the null hypothesis. Null in Old English means original, original hypothesis, all this vocabulary, okay? And in our court system, the original hypothesis is that you are innocent. HA is the alternative hypothesis. And to give you a sense of that, HA is always actually what you're trying to prove. You're trying to prove that the person is guilty. Okay, so it's really simple. HA, alternative hypothesis, is what you're always trying to prove. HO is the default position. Okay, so now if you have a lot of evidence that someone's guilty, let's say this is a murder, they were at the scene, they got blood on their clothes, they're holding a knife. Okay, you got a lot of evidence. You would reject HO. Reject HO is formal language saying, I don't think HO is true. I'm going with HA. So if you reject HO, you're basically accepting that HA is true. If you are eventually found wrong on that, like some crazy situation where some lookalike was doing that and you were wrong, that's called a type 1 error. So a type 1 error in definition is when you rejected HO and went with HA, but later found out you were wrong. Okay. A type 2 error is when you fail to reject HO. Failing to reject HO basically means we don't have enough evidence to reject this. So, in other words, if somebody brings you evidence, what's your evidence that he murdered him? I saw him 20 minutes before with that woman. Okay, that's not really good enough evidence to do anything. The burden of proof wasn't met. So if that's the case, the phrase that we use in statistics is failed to reject HO. Your evidence did not provide enough for us to move off of HO as a possible outcome. But if you failed to reject HO and you ignored HA right here, but you were wrong eventually, that's called a type 2 error. Now they're in Roman numerals. This is also called an alpha error, and this is called a beta error. So there's a lot of vocab here. Alpha error and a beta error, or a type 1, type 2 error. Obviously, A and B, 1 and 2. It makes complete sense. Okay. So now, this is from the day 2 notes, but this is how it's going to play out with p-values. Now, a p-value, if you remember what it means, it's the probability of something happening by chance if HO is true. Okay, so you assume HO is true, do some calculations, and if you get and then you get a p-value, and then you're going to do something with that. Now, if you remember, the alpha level is how much proof you need. Okay, and alpha levels are set by humans. So, and the common alpha levels are 0.01 and 0.05. Those are the common ones, although they can be anything. Now, what they are is if something is very serious and you want to really make sure you get a lot of proof before you reject HO, you want to lower alpha. My example is always in a murder trial, you can't get that wrong. So you've got to require a lot of proof. That would be lowering alpha to make it harder to prove. If this is a shoplifting case, and if you're wrong and some kid, picks trash up on the freeways for no reason and he was innocent, it doesn't ruin his life. So you can have alpha level higher. Okay, so 01 is a higher burden of proof. 05 is a less burden of proof. Okay, all these things come into play. So from a math standpoint, how you would write your conclusion, okay? If alpha's 05 and your p-value is 07, 07 is bigger than 05, so you're going to fail to reject HO. You didn't get enough evidence. Fail to reject HO. And then you'll write, there's insufficient evidence to conclude HA. Okay? Now, if you fail to reject, there is a possible type 2 error. This one, alpha's 03, weird number for alpha, but just go with it. And the p-value came in less than 0302. There's a rhyme here to help you. If the p-value is low, you reject the hoe. Okay? So the p-value 02 is less than alpha. Therefore, we reject HO and go with HA as the probable outcome. Okay? But if you do that, there is a possibility of a beta error or a type 2 error, often called a beta error. Okay? Now, there's a couple of those. Now let me go to 1C and 1C. Get 1C, 1D. Okay. All right. So here we go. For 1C, alpha is 0.1. That's a really high alpha, easy to prove. But your p-value came in bigger than that. So the p-value isn't low, it's high. So this is a failure to reject HO. You did not get enough evidence. Remember, this means there's a 22% chance we would get this data by chance, even if HO is true. Because it's higher than alpha, there's insufficient evidence to conclude HA. That's a possible type 2 error. Okay, for D, alpha is a ridiculous 0.2. Nobody would ever do that, but okay, let's just say it is. Okay. The p-value is 0.25. Again, that's failed to reject because the p-value of 0.25 is bigger than alpha. We have insufficient evidence to conclude HA. Possible, insufficient evidence is a possible type 2 error. I have a mistake here. Type 2 error, often called a beta error. Okay. Now, here we go. Alpha's 01, really low, and we got a really small p-value. We snuck in there. We do have enough evidence to conclude HA. There is sufficient evidence to conclude HA. whatever HA is in context. Now, when you write out your sentence frames, you won't say HA, you'll say what HA is in context. I don't have context here. I will soon in the next ones. So there's a possible type 1 error here, okay? This one, alpha 0.15, strange alpha level. The p-value is 0.01, reject HO. The p-value of 0.01 is less than alpha. Sufficient evidence to conclude HA. That is a possible type 1 error. Type 1 error, possible type 1 error. That's a possible alpha error. A reject is a possible alpha error. Okay, and then G, 0.5 is alpha, 0.1 is the p-value. And then this is a reject HO at alpha 0.5. And again, these are sentence frames you want to memorize and use. This is exactly what you want to know. I know it's from a previous lesson, but you want to memorize these. This is also a possible type 1 error. Alpha is a strange number. Again, alpha is always 0.5 or 0.1. I put some strange ones in here to help you out. P-value is 0.1. It does meet the criteria. Reject HO at alpha 0.12 with a p-value of 0.1. There is sufficient evidence to conclude HA. Possible type 1 error. I got a lot of mistakes here. Type 1 error. Possible alpha error. Okay? Again, alpha is set by humans. They're the ones that set that up. And it's one of those things that's debated in the courtroom. A lot of times the judge will say, you know, what level of proof are we after? Like if it's a murder trial, it's kind of beyond a reasonable doubt. Shoplifting is just kind of like it's probable that they did it. Those words have meanings in terms of numbers, okay? And this is something as a lawyer you'd have to handle this type of language. All right, here we go. Alpha is 0.01, p-value is 0.05. That's a fail to reject. Remember, not enough proof. When the p-value is larger than alpha, that's not enough proof. That's a fail to reject HO. We can't conclude HA. We say insufficient evidence. That's the phrase we use. That's a type 2 error, possibly. It doesn't mean you committed these errors. It means you have a possibility of that. Remember, no matter what decision you make in life, you run the risk of being wrong. Isn't that obvious? Okay. Now here's one. 07 and 07. What do you do on that? Typically, if it's the same thing, that's insufficient evidence. That's going to be a possible type 2 error. Okay. Fail to reject possible. That's a beta error. Okay. All right. So I exhausted that to death. That's quite a bit. Now, understanding the power of a significance test. Okay, power of a test. Hang on. Okay, got it. Power of a test. Now, you really need to understand a couple things, and I would write this as I'm writing this to you. You got to understand the relationship between alpha, beta, and sample size. Okay, this is something you have to understand. Okay, as you lower alpha, if alpha goes from 0.05, okay, to 0.01, what's going to happen is you're going to increase the chances of a type 2 error, a beta error. Because as you lower alpha, it gets harder to prove. You get more fail to rejects when you lower alpha. More fail to rejects result in possibly more beta errors. If you raise alpha from 0.1 to 0.5, the reverse is going to happen. You're going to make things easier to prove. Things that are easier to prove have more rejections. But if you do that, you're going to increase alpha errors. You will decrease beta errors in this. And by the way, you can never get it perfect. You can't. If you want to eliminate alpha errors, okay, then you're going to increase beta errors. If you want to minimize, if you want to minimize beta errors, you're going to increase alpha errors. It's just the way it is. Think about just a court system. If you want to catch every murderer, every single one of them, all you got to do is make it easier to prove, and you'll catch them all. But the problem is you will also catch people that didn't do it. If you want to never put somebody in jail that did anything right, didn't do anything wrong, then you're going to make it things harder to prove. So you'll never make the mistake of putting an innocent man in jail, but you'll also never put anybody in jail. That's the balance you have to have between alpha and beta errors. Now, n is sample size. The more samples you have, the fewer errors you make in general. So if n goes up, alpha and beta both go down if you have more samples, because more samples means more proof. When you have more proof, you make better decisions and you simply make less errors. I hope that makes sense. The word power, back to the notes, is a test's ability to detect a false HO. Okay. If you're the ability to detect a false HO relies on a lot of things. Okay. The ability to detect a false HO is it's mathematically it's one minus is the complement of a type 2 error, one minus beta. So it's one minus beta. Okay. Now, also the power of a test goes up when you increase samples and when you increase alpha. So if you make something easier to prove by increasing alpha and you get more evidence, more samples, that test is more powerful. Okay, that's the main thing you got to get out of that. I know this is very complicated. All right, let's try to go on to some examples here. Have your calculator ready. All right, here's a claim. Drug company claims, I'm on 3A here. Drug company claims that people suffer side effects from a cholesterol drug 8% of the time. 150 people were asked, and 18 had the side effect. That's 12%. Now, I know 12% is higher than 8%, but remember, every time we do a study, we're going to get a slightly different result. Is 18 out of 150 a large enough percentage to conclude that that claim is wrong? Or could 18 out of 150 have happened by chance just within this sample? That's the question you're going to ask. So the four-step process of writing a hypothesis test goes like this. First thing is you got to write HO and HA. HO is the claim that the percentage is 8%. HA is what you're trying to prove. We believe it's more than 8%. Okay. Now, remember the assumptions we wrote for the confidence intervals? They're back. Okay. This is the SPIN acronym. Please write, assume the following or assume that representative sample of test takers, drug takers, 10 times. Each reaction to the drug is independent, and then check this one to see if we have a normal curve. Okay, n times p and n times 1 minus p. Now, the next part, this part right here, we're going to do this on the calculator. Okay, your test statistic, which you can do an interval or the test statistic. You can do either one. Okay, let's do the test statistic, but on the calculator. Okay, here we go. You're going to go stat, and you're going to go over to tests. And then you're going to do a one prop z test. Now, a one prop z test is related to one prop z interval. Okay. The claim is 8% have the side effect. 18 out of the 150 said they had the side effect. And here is HA is greater than. Okay. So what we're going to do is we're going to do this, draw it out. And we got a z-score and a p-value. The z-score is 1.8. The p-value is 0.0355. This is what you're going to write out. And what you're actually going to write out is the standard deviation is going to be right here. It's going to be 0.08, what was it? 0.12, 0.12, 0.88 over 150. There's your standard deviation, okay? And then you're going to shade this area. This is 0.03. This means there is a 3.55% chance that we would get data this extreme even if HO is true. So this wouldn't happen very often if HO is true, wouldn't. Okay, so let's see how this plays out, okay? Elopes. Okay, so notice here is the, here's this right here. There's 0.0355. Now, what's alpha? Let me look at the directions again. Alpha was, it doesn't say what alpha is, so we're going to just pick one, okay? If we pick 0.5, it's a reject. If we picked 0.1, it'd be fail to reject. So if you are the drug maker company, you want 0.1 because you want this hard to prove. You don't want problems. If you're a consumer group, you want 0.5, saying this is easier to prove. So it is a reject at 0.5 because the p-value is less than alpha. We have sufficient evidence to include HA. Now, this is the last chapter. If you wanted to do a confidence interval, this would be it. Now, a confidence interval, this would be 90% interval. The reason it would be 90% is because if you do 0.5, okay, you have to double it because this is called a one-sided test. A one-sided test is a test that's greater than or less than. So we're going to double this and make it 0.1 and go 100 minus. Notice the interval does not have 8% in it. It's slightly higher than 8% and goes all the way to 15. But 8% is not in there. That means you can reject the idea that it's 8% with the side effect. It's probably more, okay? However, because you're rejected, you do run the risk of a type 1 error, okay? So there's one of those. All right, next one. Okay, casino game, Wheel of Wrath claims that the cash prize of $100 or more is awarded 30% of the time. However, a gambler tracked the last 80 spins and noticed there was only 21 cash prizes of that. It's a casino game inflating their proportion of wins. All right, so the statistic came in at 0.2625. That's really pretty close to 30%. I don't think we're going to get enough proof here because that's pretty close to 30%. Okay, your HO, P is 0.3 or P is less than 0.3, meaning they're inflating their wins. This is your SPIN acronym. You should know how to do that by now. We have to meet a certain number of samples down here, and we have to meet the criteria for running a legitimate study. Now, again, this next part, the test statistic that we're going to run right here, this is something you can do on your calculator, okay? So we're going to go to the calculator again. We're going to go stat tests, one prop z test. This is a proportion. And the claim was 0.30, and we got 21 out of 80 that actually happened in our study. Is that enough evidence that it's less than 30%? There's your less than. And this is great that you can do this so quick. So the math's pretty easy. Here we go. And well, look at that z-score is negative 0.7. The p-value is 0.2321. There's a 23% chance we would get something this extreme even if HO is true. That would happen quite often if it was 30%. So there's no proof here. There's none at all. Okay, and you can see that that's what came out in this right here. Okay, now if you wanted to do a confidence interval, again, if we did a one-sided test, I'm going to 90% interval. Notice that 30% is in the interval. So 30% is a viable answer to the prompt, okay? Now, you wouldn't do both this and this. I'm just trying to compare what you guys are learning now with what we just got done doing. So this is a fail to reject at 0.5. Because the p-value is high, we have insufficient evidence to conclude that HA is true. But if we could be wrong, this does run the risk of a type 2 error. Okay? All right. We've got a couple more to do. Yeah, C and D here. Okay, so here's C. Okay. Protein powder complains that each serving of their shake contains 40 grams of protein. Okay, now this is a means test. A random sample of 31 contain an average of 38.7 standard deviation. Is there evidence to suggest the company falsified their claims? All right, this is not a proportion. This is a mean. Okay, so HO, the claim is 40. You think it's less than 40. You think it's this, okay? Again, here are our assumptions. Because we have a large sample size, the CLT will ensure normality, but you guys should know how to do these by now. Now, this is a little different. This is a test for a mean. So we are going to go to our calculator and go stat tests, and we're going to run a t-test. Very similar to a t-interval, okay? So the claim is 40, correct? And let me look at, what was it? 38.7, 4.6, 31. Okay. So X bar was 38.7. I keep forgetting what I just did. 38.7. Yeah, 38.7. Standard deviation was 4.6, and it was 31 samples. Okay. And we're thinking it's less than. That's why that claim is less. Let's go ahead and draw this out. Okay. Bam. So this comes up 0.063. So there is a 6% chance we would get data like this. So that's not really great proof. Okay, it is more than 5%. So again, if we're looking at this, okay, check it out. We got 0.06 here. Now, if we did a confidence interval, a 90% confidence interval, degrees of freedom 30, this is the previous chapter, we would get this. Notice that 40 is barely in the interval. This data that we obtained did not provide enough evidence that their claim is incorrect. It could still be 40, even though in this set of 31 samples, the average was 38.6. It could just be one of those things that happened. This is a fail to reject because the p-value is greater than alpha right here. However, we are running the risk of a type 2 error. Okay? All right, last one. Again, another mean here. Does living on campus benefit a student's GPA? My daughter lived on campus and loved it. Because of housing shortages, half of 70 students were randomly assigned to live on campus first semester. The other had to live at home. For the second semester, they switched. Does the data suggest that living on campus is better or not? Now, this is called a match pairs test because you're looking at the difference right here. So what you're trying to figure out, these are the numbers we want. So if you're on campus, this was your GPA, off campus is here. If those numbers were exactly the same, then the difference would be 0. And a difference of 0 proves nothing. However, there is a difference. The GPA was 0.23 higher when living on campus. Is that enough to prove that living on campus is better? Well, the null hypothesis is going to be mu sub difference equals 0. This is something you got to get used to, sub difference, because we're talking about the difference between these two. And HA, mu sub difference is greater than 0. I'll put the 0 in there. Got to put that. Here we go. Your assumptions, we know how to do that, okay? So let's go and get that written out. Now let's go to our calculators. And we get these numbers memorized. 0.23, 0.896, and 70 people. All right, so Let's go to the calculator. Stat, tests, t-test. Okay, 0 is the reference number. Okay, 0. And this was 0.23 was the average difference. And then 0.896 is the next one here. 0.896. And then this was 70. So is that's probably going to work. I think it's going to be enough proof. We're thinking that it's greater because the being on campus helps. Okay. And you're going to click draw right there. This may come out really small. Yeah, it's pretty good. 0.0176. So it's not enough proof at the 01 level, but it is enough proof at the 05 level. So you can pick either one. I went ahead and went with the 05 level. So you can see that, again, if you look in here, there is the answer to what we did. This is the confidence interval right there. So 0 is not in the interval. So there is a slight, it might be very slight, but there's something to it living on campus. So this study does reject HO at 05 because the p-value was low. There is sufficient evidence to conclude HA. And when you reject HO, you do run the risk of a type 1 error. Okay, there's a lot there. This might be a very handy video for you guys to look at later. And we will do all kinds of problems in the immediate, okay? So we'll leave it at that. All right, that's it, Stat Nation. That is chapter 9, day 4. We'll see you next time.